fascinating that it would just sort of work out that way. Then it turns out you can actually calculate a wave equation for electromagnetic fields if you sort of play it a bit further mathematically, which we'll start to do by the end of the class. So in any case, today's experiment is basically going to be exploring these basic ideas. And they're very rudimentary, nothing real fancy about the measurement. But here's what I want you to think about now. If you're going to use an electrical current, just one other thing. In order for an electric charge to be known or for an electric field to be observed, what do you need?
You need a charge in the field.
You need another charge to interact with it. So if you were wanting to measure a magnetic field, what would you need to do so?
Magnet.
You need another magnet. Well, if we don't have, problem with a magnet itself is that if you took a magnet and put it in a magnetic field, it's going to change direction. That's about the only thing it's going to change, right? Or it's going to be pushed around and moved around. So, next best thing is how might you create a magnet that you could ultimately use to sense a magnetic field, another magnetic charge coil, a moving charge. Yeah, more specifically, a charge coil would work, a moving charge. So, in the simplest case, maybe a charge moving like in a straight line, easiest thing to measure. Now, if I've got a moving current in a particular direction, what's the magnetic field it's going to produce? Yeah, charge moving in this direction. What's the direction of the magnetic field? It's going to produce a magnetic field that's going to look something like this, right? So if I put another electric charge, another moving electric charge, how might I want to orient it so that I see the first one? Yeah, so I've got an electric charge, and I'm measuring a magnetic field, or I've got a magnetic field produced by it, okay? Moving electric charge. And I want to see what the behavior of this is by taking another, I don't know, just take a wire and we'll have some current flowing through it, call it I naught or something. What direction would I want this to be oriented so that I would get a response between this moving charge and this one? The other way. What would I want the magnetic fields between the two things to do?
Go in opposite directions.
I'd want the magnetic fields to be parallel. Because the magnetic field here, if it's produced by a moving charge, guess what it interacts with? Another moving charge. Just like an electric charge produces an electric field, what does it interact with? Another electric charge. A moving charge produces a magnetic field. Guess what it interacts with physically? How do you know it's there? Another moving electric charge. So in a way, it's equal but opposite, not equal or opposite, but opposing magnetic fields, each acting on the other. So I take a moving charge, and this produces some magnetic field. This magnetic field will interact with this as this magnetic field interacts with this in order to see it. Well, I wanted to sort of draw it spatially this way. It doesn't necessarily matter if it's parallel or anti-parallel. The bottom line is they need to be aligned in such a way that they'll affect each other in a usable fashion. Now the reason for that becomes, well, it's not so obvious now, but this is where this is sort of important. So to this end, then, if I wanted to measure this current, I would want to place a current parallel to this magnetic field. Or at least oriented in such a way that it will interact with it. And usually the requirement is, whatever I use for a sensor, a magnetic field sensor, will almost always have an electric current built into it. And the key is, however you apply that sensor, the best response you'll get will be when the current in the sensor, or the response of the current in the sensor, acts perpendicular to the magnetic field. So you've always got these perpendicular relationships. The current produces a perpendicularly oriented, normal-oriented magnetic field. And that magnetic field will interact with a perpendicular moving current. So everything that we thought of along same directions, now we have to think of in terms of three-dimensional normal directions. Kind of like torque. It's a vector, so you can orient it in any possible way, but the closer these are to each other, the greater the interaction of one with the other. So if you look at your magnetic field devices, and this is what's kind of interesting, take out in your kit, the only thing you'll need, I think, out of your kits, besides maybe a couple connected wires, is a magnetic field sensor in there. And I want to show you this thing, because this is kind of cool and it's important to how we have to do our measurements.
It's out there.
Sounds good.
It's out there,
I have no idea where the term B originally came from. As a letter, you'd think it would be M or something, right? A big M or something.
I'm just thinking that it's perpendicular.
Charge.
Could be wrong, but I'm thinking that's a lot like the binomial vector.
So is it person?
Oh God, I don't even remember the binomial vector. Binormal, is it binormal?
Yeah.
But yeah, it probably is. It probably is. But I can't say for certain.
Magnetic field.
One direction it's cosine, one side, and the other side it's just with time, it's creating a spiral.
That's probably, there's probably a
At any specific point, if you find the binomial vector, it'll be directly perpendicular to that.
And probably what happened is this phenomenon was observed and summarized physically, simultaneously with, in the time frame of vector calculus. And so there were a lot of things happening simultaneously. So somebody working with mathematical relationships might find this sort of orientation as a binormal orientation. And this field, which I don't know what it is, would be a binormal field relative to the phenomena that generated it. And they're made very, I'd never even heard that before. If that turns out to be the case, that's amazing observation.
Yeah, well, I just remember, that would come by, show the normal vectors, come to the tangent exactly toward the curve at that point. So it looks a lot like that.
Oh, yes. Now, the chicken or the egg, I'm not sure. But yes, absolutely they're related.
This one over here.
Of course, kidding me? I had to bring a substitute in yesterday, a substitute kernel. So, okay, when you take out your field sensor, pull that little sucker out for a second, 'cause I want you to see it. This is the most amazing device.
It is.
Okay, this little device is called a Hall field sensor, or a Hall sensor. The way it works is seriously funky. So, the idea is, if you look inside this thing, there's a little power supply. It runs the current. It runs a current from in a certain particular orientation. This is within the device itself. So here's your wand, and this is your device. Now, when you put this in a magnetic field, the magnetic field is going to interact with this moving charge And if the moving charge is free to move. It's not in a wire, it's actually in a plane. Like a flat copper piece of wire, so it's not a round, tiny wire, it's more like a flat conductor. So you've got current flowing this way. Now, if you run a magnetic field perpendicular to this current, say out of the board, it will bend the current in one direction or the other. And by bending the current, it will produce, say you bend it in one direction, it will produce a potential difference laterally to the original direction of the current. And that potential difference, which is related to the amount of current that flows from one end to the other, or laterally, is directly proportional to the magnetic field. So when you have a magnetic field that's outward or inward, what you will have is you'll either have a deflection of current in one direction or the other, and a corresponding induced voltage that's perpendicular to the direction the current was flowing otherwise. So we've never talked about that, having a wire that has current flowing one way and putting a battery perpendicular to that. We've never had to deal with that. But there's no reason why you can't have current flowing in two directions simultaneously, or some aggregate electric field in some opposing angle, or some off angle. So this is called a Hall sensor, or a Hall effect sensor. And this is what our magnetic field sensors are. It's the only way we can do it to measure actual magnitudes of electric field, or magnetic field, because this induced voltage, lateral voltage, if you will, Hall potential, we sometimes call it, is directly proportional to the field that's bending. So to that end, as you look at your device, normally we think of a probe like a rectal thermometer. You just take the damn thing and you just poke it in, right? We can't do that with these devices. The way the device works is, if you'll notice on the end of the wand, there's a little white circle. I'm all flustered now. You got a resistor in there. So I think resistor. I made that up when I was writing the exam. It's like, yeah, he's got a load. Sometimes he goes to the bathroom, he carries a load in his diaper. A loaded rooster.
You had to cool them up.
Yeah, well, that one's kind of an old one, but the other one I made up, I thought it was cute. You'd have to have a bird thing to understand. So the idea is, in order to measure the magnitude of a magnetic field, you want to orient the face, which has that little white dot on it, lateral or normal to the direction of the magnetic field. Or if you will, if you take it and rotate it in space, if you rotate it and measure the magnetic field and its maximum at a particular rotation, then that implies that the magnetic field magnitude is along that direction, and the value measured is the value of the field. So it's just kind of cool to be able to do that, but I wanted you to see, it's not like you just poke it in there and the sensor's on the end sticking out like a wand or something. It's actually lateral. So when you measure sideways to the field you're producing. Because everything is at a 90-degree angle with magnetic anything. She's just kind of wild. So anyway, I'll let you guys get to work. I know I talked a bit, but we haven't gotten through this stuff, so I want to give a very deep context for this stuff. Hello, Berto. What's up, dude? You're back to you again, huh? He's dance with you, yeah? And there's a lady at the table, and I know you like the ladies. Yeah. I don't know if she'll like you, but he does. He likes the chicks.
Yeah.
Remember, Audrina? Oh boy, he was all over that. You had left early. I think I mentioned that. You'd left early. To you. And he was over there and he was crowing at her when she'd turn her back on him. And he would just coo and sit right next to her and just coo.
We have 4 chicks at home right now that are
You do?
2 weeks old, yeah.
Oh my goodness.
I hope we don't have any roosters.
I'm not prepared for having an
That's the
indoor
thing.
rooster.
It's it sucks.
You got a yardstick over here.
He doesn't hear me, because he's my second rooster. The
He's your
first-
second rooster?
He's my second. I actually had a hen as my first, and a rooster came after that. And then,
Oh, I thought you thought this was a parrot or something.
wait, see, no, that actually got. He was the third one that I got, but I got him much later when the other two were fully grown, in the hopes that they might adopt him. They wouldn't.
They'd either adopt him or the male would try to poke his eyes out or something.
Exactly, and that's exactly what happened. The male.
Ooh, I got your
Stuff,
tail. Look
right.
at that. I got your tail.
I gave the other two birds away, and I had to give the other two birds away, and he stayed with me.
You chose him over two other birds?
Well, my first two other birds, there I got, they're a pair already, so so I couldn't leave this guy alone. I couldn't give him away, and
He was the baby.
he's the latest one. I feel bad giving away my hen. Like my first rooster, I didn't really care too much about. He hated me. I didn't like him.
Is this million?
No, the 10 amp.
Okay,
Yeah.
not millions.
Ours are so
And by the way, you always measure current in what
He's had-
orientation in a circuit.
He's been kind of sad actually because he
Series.
misses everybody.
Always series,
He really likes
never
being
parallel.
in the fly.
Because it basically shorts the circuit
He's a
and
big
draws
guy.
current
Right.
away from where it would otherwise go. Lowers the voltage,
Everything goes.
draws tons of current. The kilogram more comes, at least in the basic sense, comes from just its relationship.
We're just using our natural.
I guess you could say it's a kilogram meter actually goes away. The second goes away, and you're left with basically a coulomb second. Yeah, and what that means, I have no idea as I look at it, but there's probably something extremely profound there, or kilograms per second. Mass flow.
Here, pull on it.
Okay.
That's connected to the monitor. I think, if I'm pulling on the same one as you.
Certain amount of mass
That's the
per
monitor.
second.
Maybe it's not supposed to be in the monitor. What if I unplug it?
Now that you do
Oh, no, that needs to be plugged in.
for
Crap. Here, can I? Can you try to plug this back in?
It's like probably tugging on it down. Find it.
magnetic cords.
That would plug it. You got it? Yeah. That's a monitor.
So there is a force acceleration built into it.
Well, it's not, yeah, the monitor went black.
You got a charge. This is like the ratio of mass movement per unit charge.
Can we use this computer?
But then we still have.
Okay, we have 5 amperes running into that stuff. Plugging the sensor.
Let's
cut to the chase.
Here, right, ow. That hurt.
That would be what would be moving. So put numbers in.
Here's you.
Equivalent of 1 times the mass of electron.
Have some Greek yogurt there, buddy.
Ooh.
There goes the
Probiotics under the roost.
And then 1 coulomb is related to.
Alright.
Coulomb is
Give it.
some number of electrons.
It's the dumbest thing.
Inverse of 1.6 times 10 to the
Okay, well, you know, one thing that we can actually say.
We ever had rooster wings? Rooster wings.
Oh, that's right. He wants me to feed him.
And what?
He wants me to feed him. He's like, he's being real sweet. Feed you later, buddy. Yeah, I'll have to do, man.
Give me some shit.
Ooh, there we go.
Yeah, all over here.
Yeah.
Right, we want like a USB, one end should look like, and look like this, the other
happening?
one's like a USB. Where's the right?
Ports that way, that one ports that way.
When we draw a line, we draw straight arrows, and at the end we draw
We're
curved
my
arrows.
first,
Straight line,
so, like,
straight arrows.
Taking these things. Okay.
What's happening, guys?
Yeah, for one electron, if you took this,
you see that perpendicular. All of a sudden, shoot it out. And then,
seconds would be the motion of one electron per second traveling along. So, so 5.68 times 10
Okay, roast.
to the 12 Tesla.
that's one
roast.
part I'm done.
So this is the electron.
Place a magnet close to the camera.
Is this our magnet?
Oh, that not a magnet. Charge when you change. Charge itself when you change. Still the charge. That is definitely a magnet. So,
Oh, hell
how many keys per second?
Good resistance. Let's take this along with it.
I could have pulled and string. Turn it up, I don't know.
Divided in.
Hey, Q. Q.
Yeah, watch the wire.
Why can't we use this one from the monitor? Why can't we use this one? Which code do we need? We need this one? Like this? Yeah, and we can plug it into the USB.
Yeah, it's close.
No?
That's the one. That's the one I was trying to ask you guys to pull.
Oh, yeah, that's the one we just. Wait a second.
Yeah, that's the
Well,
one.
it's supposed to be pulling each other.
This one?
There wasn't a track.
Yeah, that's the one.
Oh, wait, we're gonna use the other
One
computer, right?
tenth, now remember, this is.
Well, this monitor has something else.
Oh, okay, it's on.
Like, it's on. It doesn't need. I don't know why it was plugged in there. It's just,
Yeah.
it was just plugged in there for no.
I mean, you can use it if you
It
want
made
to
the
plug a
monitor go
USB
black
over here.
earlier.
No, it didn't. He unplugged it. So it could go
So
black.
what is the current?
Oh, it just happens to be unplugged. I'm sorry. Alright, I'm gonna put this back.
On your phone, it's fine.
How much resistance was there? Not enough. Alright, here we go. This is
Plug that stuff in there. Let's sort it out. Oh, that's not even hooked up. Yeah, real quick.
This is it. Per coulomb.
Alright.
Stretch the speed.
We need to zero it.
We got some sleep.
I don't know what that
We got it like,
means.
how are we gonna hold this?
How does it say how to do it? Zero.
That's the strength of the magnet. Just now.
Yeah, product of a Tesla and current, Tesla second would, in fact, absolutely correspond to 1 kilogram. Or a magnetic field producing charge. Yeah, no, that's I'm saying, you just kind of get this, it's like, oh, wow, these things have nothing to do with this sort of thing.
We're over here working.
Here's the thing about this is where it's really quite good. So when we did simple harmonic motion, we said that d, say dx squared, d squared dx dt squared is related to minus omega squared harmonic oscillator.
What else do you want?
Is this switch on the
So,
sensor on high?
this value, if it turns out, this is not really an oscillating field.
We are, the heat.
If you compare this to the equivalent
No, we don't got a budget.
with electromagnetism
Okay, so for part A, we just need the compass.
for a wave,
You're fired.
Establishing the direction of magnetic
so it is,
So we don't need
this. So,
Like this.
so the dispersion, say d
North
squared
is the
dx
top of it and south is the bottom.
is
Or
related
no,
to
that's not
1
true.
over d
So
squared
when like
North is the top of the current
e.
and south is the bottom of the current.
because
You calibrate it to zero now?
I'm not sure like what we call it.
Well,
Do we have power yet?
you got power. Damn. 0.5.
Okay, so let's see what direction.
So this implies that d is the square root.
Attempted simple.
Apply current.
Yeah, but it should be, north-south should be
So
like
apply
this.
the wave equation
Maybe we
needed for
We need a switch. That's our switch.
electricity or for waves of strength or pressure waves. That's a chapter 12. You end up getting this relationship.
See the change?
Has the value of this when you
Is that
substitute
actually
all
going,
the
yeah, that's true.
So this is like that.
That's fundamental equations that we're going to start.
It is, as long as it's me.
This south. So I mean, if you do it like this, the red one's supposed to show the north. So this is south, north. The red one's
Okay, so that's just, so it's not clear.
That's something.
Oh, yes.
Crank it up.
So it looks like this.
Set the switch on the sensor to high.
Your wire.
The thing
The
is,
sensor actually
go this direction.
2 milliTeslas.
Let's make sure our switch is off though. We'll put it together. These are the compass sketch out the direction of the magnetic field associated with the signal. There are various objects.
No, it's totally obvious, right?
Multimeter's not giving me any readings or.
But is that what it says?
Okay, well,
Because it's.
So let's test it right now before we.
No,
only if
that's, it goes from the, I mean, isn't the charge goes from positive to the negative, right? So this is how we rotate. If that's the direction of the movement, that's how it's at. Well, that's how they rotate, so the direction of the
And
movement
this
is
room
this.
is miserable for magnetic
Actually,
field.
it's
You can't
charged,
find
actually.
magnetic north in this room because of all of the wiring around the room.
No, it goes from the negative to positive, and the
Well,
electrons
like when we solved this,
What if we treat it like it's that, but the actual movement.
When I get under it.
The drift.
No, like this.
Well, no, that's when we calculate.
Why can't we get?
But like, you know, but I'm thinking about like.
it's going exactly perpendicular. The more you increase it.
that's why the circuit.
So is it still
Measuring zero.
So you're gonna use 2 millimeters?
Oh, you're not measuring it.
Maybe this thing is
it's going out,
Yeah, it's just gonna
See
be.
if you put it over here, it goes like this, right? So as you Okay.
This thing?
And we can put it aside.
Okay, this is a lot of metal.
Turn it on, I wanna see if there's actual stuff. This is not, turn it on.
Okay. Negative to positive.
No, it doesn't block wires, so we technically don't want it, 'cause you saw it.
Yeah, I think I look at it, so it goes from here to here, all the way to there. So it goes from this side to that side, this
Okay,
side.
motion positive to the ammeter to the
Series of kids.
slinky. Slinky goes to the negative.
Only holes that will produce five.
So this is the plus end, and this is the negative.
Yeah, and this is works like a switch beside.
Yeah.
I'm not
This is
seeing,
positive.
there isn't a circuit.
Are you? Put it on this. Put it on this.
Yeah, it's circuits. Completed, yes.
Break it up a little
You gonna bite me?
Basically,
That wouldn't feel good.
Huh?
You gonna bite me? Feel good?
Only if you have a freckle. We'll go after freckles.
You like freckles?
Our chicks go after freckles.
Well, there could be a case of bad wires in them, too.
I made it.
Remember how that was going?
I'm surprised. They're the best person ever. They're so adorable. And they're so young, they would like.
can't
all
see it
four
from the
of them would
side
fall
very well,
asleep in my
what's
lap.
happening is the same. It's got a
Yeah, as soon as I got him, like, I wanted to get a little heating vibes, but he didn't want to stay in there, so
You just cuddle.
he stayed with me every night.
Which is why the red.
That's great. I would have done that happily too, but I think
You guys what are we
you
doing?
have to.
This wire for.
I'm confused because
Okay, here's 0.5. You calibrate the sensor? No? Let's see. Oh, look, bro. Actually, the sensor is white, not
It doesn't give you value, it only gives you direction. It shows you what direction physically you're going. So it's a perfect vector to go.
Do a series, so we
I used to use these little things that those little hoops. We used to, yeah, galvanometers. We used to use those to measure magnetic field, to calculate the magnetic field north, the actual magnitude of it. The problem is it doesn't work right in this room because the compass doesn't line up with magnetic north. So you can measure whatever the net field is of it. But it won't tell you anything about magnetic north.
yes, that's not.
Yeah, you take that compass and walk around the room and the thing does this. It's just ridiculous.
But this is.
Lights, everything.
Oh, you know what? We got.
Should we be getting a different compass reading if whether the compass is like inside the slinky or outside?
know.
Positive goes in.
Okay, you probably want to calibrate. We have nothing to calibrate with. Can't see this.
Negative.
But what we will need to
That goes
do
into that.
is hold it away. So we'll put it in there. Is there any current flowing right now?
Yeah.
Okay, before that.